Yes, screen is visible. Students?
No, sir.
No, sir.
Yes, now it is visible.
Yes, sir.
Okay. Yes. Yesterday, what we discussed in last class? Do you remember or not? So do you have any?
Derivation.
Okay. So derivation of what?
Probability of existence of whole.
Okay. So yesterday we discussed about the carrier concentration of intrinsic semiconductor. Intrinsic semiconductor, and that two parts are there. So first one is the calculation of density of electrons. Second one is the calculation of density of holes. Okay. For finding the intrinsic carrier concentration. For finding the intrinsic carrier concentration, there are two parts are there. One is the first we have to find out the calculation of density of electrons. Okay. Second one is the calculation of density of holes. Okay. So now for that, so just initially particular energy range, how many number of electrons will be there. So density of electrons we will calculate, that is dn. Okay, if you integrate it, you can get the total number of electrons. Here Z of E dE is the energy density of the states. Density of the states. F of E is the probability of finding the electron. Okay, so how we will calculate the probability of finding the electron means by using Fermi-Dirac function. Fermi-Dirac function. Okay, now so by using that function here, so we are calculate the, so this is the, you have to remember basic formula for density of the states. Density of the states. Okay, in the energy interval E and E plus dE. Okay, so now you have to remember this formula. So you have to apply this formula. You can in all cases, in case of intrinsic semiconductor as well as extrinsic semiconductors also. Okay, so in intrinsic semiconductors, electrons and holes will be there now. So on that, so instead of mass of the electrons, what we will do here, so here in place of m we have to do the mass of the electron. So and similarly in place of the energy value we have to take the effective mass of the electron. Effective mass of the electron. Similarly for holes also. Okay, in place of mass of the, here m, mass of the hole we will take. So in place of energy we will take the, so energy, effective energy of the hole. Effective energy of the hole already we discussed. So what is the effective energy also? Okay, so the kinetic energy of the electron is approximately so equal to the effective energy of the electron. Okay, so like that, if you this is the Fermi level here, that means by using this Fermi level, so Fermi energy, so f of e Fermi distribution function, this is. So by using this Fermi distribution function we can find out the probability of finding the electron. Okay, so for electron, so this is the probability of finding the electron. Okay, in case of density of electrons. Okay, so if you simplify it, so because here E minus F is very greater than KT. Okay, that's why, so what we are taking, so this value is very high, so that's why we are neglecting 1 here. Okay, so that's why F of E, if you simplify it, we can get the F of E value, this one. Okay, now if you substitute the Z of E, F of E values, so we can get the, so density of electrons. Okay, so here we are using one formula. So that formula is, instead of here E minus EC, we are taking X. If you substituting that X value here, so we can get so this formula like this, so this is the integration. So integration of x power 1 by 2 into exponential of minus x by kt dx. So that means minus ax dx, minus ax dx means so this formula we can uh, integration of this formula will be so root pi by 2a power 3 by 2, 2a power 3 by 2. Okay, so here instead of a we are taking 1 by kt. If you substitute that value means we can get so that integration value will be like this. Okay, if you substitute that integration value, so we can get the so energy, what is that, density of the electrons, density of the electrons. Okay, so this is the here this total term is constant here, so that term we will take nc, that is the effective density of the states. Okay, so now density of the electrons nc is equal to this will be. Okay, now similarly calculation of the density of the holes. So whatever we are doing previously, same like that only. Okay, so z of e value is same, and instead of f of e we are taking 1 minus f of e. So why we are taking means holes, probability of holes we have to calculate. So f of e means so probability of electrons, probability of electrons. That means holes is nothing but how holes will be formed means so vacant sites of electrons, vacant sites of electrons. That means if you will take 1 minus f of e, so we can get the holes probability, holes probability. Okay, so here z of e de, density of the holes. So instead of m we are taking the mass of the hole, effective mass of the hole, and instead of e we are taking the effective energy of the electron, effective energy of the electron. This is the density of holes. Okay, density of density of the energy states of holes, energy states of holes. Okay, now probability. So this probability means 1 minus f of e. Okay, one more consideration what we have to take here. So e minus ef, e minus ef is less than kt, e minus ef is less than kt. So that's why see here this value will become small, this value will become small. Okay, that's why so we can write this simply, we can write into 1 plus exponential of e minus f by kt whole power minus 1. Okay, so now what we are considering here, this value will become exponential value will become small. Okay, if the exponential value will become small means so this will be like a 1 plus x whole power minus 1, 1 plus x whole power minus 1. Okay, so if you expand it, if you expand it, how we can get so 1 plus x plus sorry 1 minus x plus x square minus x cube, like that, that expansion will be. Okay, so instead of x we are substituting e minus exponential of e minus ef by kt. Okay, so we are neglecting here higher order terms because so 1 plus x square x plus sorry 1 minus x plus x squared. So that means here x value will be small. That means x square value will be very, very small. So that's why we can neglect the higher order terms, higher order terms. Okay, so that's why simply so this instead of this total value what we are writing here 1 minus x, 1 minus x. Okay, so if you multiply the minus inside, minus 1 plus x, x is nothing but this total value. Okay, so if you neglect the higher value, simply if so 1 gets cancelled, 1 minus f of e is equal to exponential of e minus ef by kt. Okay, so did you understood how we are writing 1 minus f of e? Is there any doubt on this? Students, is there any doubt on this? Yeah, so now we are going for further. So now we are substituting the z of e 1 minus f of e de value. Okay, so z of e value we know that so already we substituted previously. So and 1 minus f of e value we are substituting here. Okay, so already we discussed a simplification about this. Okay, so what we are doing means E minus EF. E minus EF is there. So we are getting this formula into, so like whatever the constant, another multiplication term is there here, EV minus E, EV minus E. So similarly, that exponential term also we can bring like that form, like that form. Okay, exponential of EV minus E we have to make. We have to make. For that, what I am doing means I am just adding with the EV and so minus EV, minus EV. Okay, so what we have to keep inside means, so exponential of EV minus E we have to keep. EV minus E we have to keep inside. Okay, so for that, what I am doing here, so that means so this EV I am keeping here and this E I am keeping here only inside the integration. So remaining I am keeping out. Okay, so what is that remaining? So this EV and EF. Okay, EV minus EF by KT I am keeping outside. So remaining exponential term, what is that? E minus EV by KT. I am taking minus common here. Exponential of EV minus E by KT. If you will take minus common. Okay, so this is the, so one form. Okay, let us take here EV minus E is equal to X. EV minus E is equal to X. Okay, we take EV minus E is equal to X. So what is that? If you differentiate both sides, so d is will become minus dx. d will become minus dx. Okay, and limits also, upper limit, lower limit, how it will be changed. Okay, so previously, so this lower limit is minus infinite, minus infinite. Okay, so now also what happened, instead of what we are doing is substituting, instead of E, EV. So instead of E in this formula. Okay, in this formula. Okay, what we are doing here, instead of E we are substituting minus infinity, minus infinity. Now X will become infinite. Now X will become infinite. Similarly upper limit will become, so instead of E we are substituting EV. So upper limit will become X tends to 0, X tends to 0. So here instead of EV, so we are substituting here, so this value. Okay, so upper limit will become 0 here, lower limit will become so infinite, lower limit will become infinite. Okay, now this term will be X, X into exponential of minus X by KT into, instead of DE, so what we are getting here, minus DX, minus DX. Okay, so here minus will be there. So minus will be there means if you change the limits, minus will be cancelled. If you change the limits, so what happen if minus, so upper limit will become so lower, lower limit will become upper. Okay, now 0 to infinity. So minus is cancelled. So that's why it will become 0 to infinity into x power 1 by 2 exponential of minus x by kt into dx. Okay, so this is the form. Finally we got the this type of form. Same previously whatever it will be there, same formula like that only we are applying here. So what is the formula? So root pi by 2a power 3 by 2. Okay, so what is a here? So k 1 by kt. Okay, if you substitute that value here, kt power 3 by 2 into root pi by 2. Okay, if you simplify that, so we can get, so p is equal to 2 into 2 pi mh star kt by h square whole power 3 by 2 into exponential of, here in the above equation we are taking minus common, ef minus ev by kt. Okay, so this is the density of holes, density of holes. Okay, and now this total term is constant. Instead of the total time I am taking nv. Nv is the effective density of the states, effective density of the states. Okay, now density of holes, p is equal to nv into exponential of minus ef minus ev by kt. This is the density of holes, density of holes. Okay, now we are calculating here intrinsic carrier concentration. Intrinsic carrier concentration. What is the intrinsic carrier concentration means? Ni square. Ni square is equal to n Ni square formula for intrinsic carrier concentration. Okay, here n equal 3 approximately. Okay, now so that's why here if you substitute the n and p value, that for ni will become, so ni is equal to under root of, if you substituting both n and p values, n is the energy density of electrons, p is the energy density of holes. If you substitute both, so if you simplify it, we can get this equation. Okay, so here, so 2 pi kt is common, 2 pi kt by h square is common for both, okay, so that's why here also 2 pi kt by h square will be there. So we can write that value into outside the root as easily. Okay, 2 also 2 times will be there, we can write outside. So 2 into 2 pi kt by h square whole power 3 by 2, and here me power 3 by 2 and mh power 3 by 2 will be there. Okay, so and root means 1 by 2. Okay, so now what it will become, me into mh whole power 3 by 4, and so here exponential terms. So exponential terms, what it will be there, exponential of ef minus ec by kt, here exponential of ev minus ef by kt. Okay, so here both are multiplication, e power something into e power a into e power b, so we can write e power a plus b, so if you apply that formula, so what we will write, exponential of, okay, if you simplify it, ef gets cancelled, so remaining term is ev minus ec by 2 kt, so this is the, so after simplifying, so that means here ev minus ec by kt will be there, and root will be there, means whole power 1 by 2, whole power 1 by 2 means how we can write, e power a whole power b, means e power a into b we can write like that. So here e power exponential of ev minus ec by kt whole power 1 by 2 is there. So 1 by 2 is there, means we can write in denominator 2. Okay, so this is the simplification of exponential term. Okay, here, yeah, see here, ev minus ec, means it gives the energy value. What is that energy gap between the what is that valency band and conduction band. So this is ev means, so upper limit of the valency band, ec means lower limit of the conduction band. If you will take minus common here, ec minus ev, means so lower limit of the conduction band, ev means upper limit of the valence band. So that means this, if you what is the subtraction between the ec and ev, that gives a band gap. Okay, so if you substitute, band gap is eg, that band gap value is eg. Okay, so that eg value substitute here. Okay, so that means now carrier concentration, that in case of intrinsic semiconductor, ni is equal to, so this value, okay, now okay, now we are calculating the Fermi level. In case of intrinsic semiconductor. What is the Fermi level? How it will be depends on. Okay, so above one is the, this is a very important one. This is the carrier concentration of intrinsic semiconductor. Okay, first you have to calculate the n value, and then you have to calculate the p value. Now we have to substitute the that n value and p value in this equation. Finally, we will get the carrier concentration in case of intrinsic semiconductor. Okay, that is carrier concentration in case of intrinsic semiconductor. Now we will find out the equal to p. Now in case of intrinsic semiconductor, n equal to p. Okay, so here n is equal, so already we know that we calculate the n value, and so p value, this is the p value. Okay, we are substituting both n and p value. Okay, now we are equating both terms. Okay, here some terms will be gets cancelled. Okay, what are the those terms cancelled here? So 2 is common in both sides, 2 will be get cancelled each other, and so 2 pi kt by h square whole power 3 by 2. Okay, here also 2 pi kt by h square whole power 3 by 2. So both will get cancelled. What is the remaining term here? Me power 3 by 2. me power 3 by 2 is remaining term. Similarly here mh power 3 by 2 is the remaining term. Okay, so now so bring that, yeah, so bring that the common term, yeah, one more here. So this exponential ef minus ec by kt, and here ev minus ef by kt. So bring that this term this side, this term this side. Okay, if you simplify it, so that means it is in denominator, it is exponential term is in denominator. Now so exponential of ev minus ef by kt, so minus ef minus ec by kt we can write, ef minus ec by kt we can write. Okay, so now here whatever the terms added and what is the term subtracted means here, so this is minus ef again, so this is minus ef, so here it will become so minus 2ef, so remaining term is so ev and so plus ec, okay. So here exponential term is minus 2ef, in by kt into, so what we can write, exponential of ev plus ec by kt we can write, ev plus ec by kt we can write. Okay, keep, so send that, so this side that exponential 2ef by kt. Okay, so it will become 1 by, okay, 1 by minus 2ef by kt. Okay, if it will come into numerator means it will become exponential of 2ef by kt. Okay, so if you simplify it, mh star by me star whole power 3 by 2 into only remaining term these two. Okay, that's why if you simplify it, so these two terms will become mh star by me star whole power 3 by 2 into exponential of ev plus ec by kt. Okay, so after simplification we will get this one. So now apply the logarithm both side. Now we will apply the logarithm both side. If you apply the logarithm both side means okay, here this is e power x, if you apply log, so log e power some constant value, e power x value. So if you apply log means, so this is the we are applying logarithm, that's why e power x and log e, so it will become so only x, only whatever the x will be there, that only it will comes. Okay, so that why e 2ef by kt, 2f by kt we will get. Okay, now so we are applying the here log, so this total term we are applying the log, so log ab, this is a term, this is b term, so log a into this is the log a into b. Okay, so we can write log a plus log b, log a plus log b. Okay, now we are applying, yeah, see here, so log a, so we are applying for this, so log of mh by me whole power 3 by 2. Okay, so log a whole power n will be there, so how we can write, n into log a we can write. Okay, like that, so 3 by 2 into log of mh by me. Similarly, so we are applying this term for log, what happened, so exponential get cancelled, simply ev plus ec by kt, okay. So after applying the log, so we can get this value, this value from this equation. We are calculating ef, Fermi level, ef is equal to, yeah, so send this kt this side, 3 kt by, so send this to this side, 4, 3 kt by 4 into, okay, so ln of mh by me, ln of mh by me. Okay, and this kt also multiple for this term also, and this 2 also multiple for this also. Okay, that's why, so it will become, so ev plus ec, so kt gets cancelled, so by 2. Okay, this is the Fermi level of intrinsic semiconductor, this is the equation for Fermi level of intrinsic semiconductor. See here, now at absolute temperature, if you will take absolute temperature means 0 kelvins, so what we are getting here, me is equal to mh, mass of the electron equal to mass of the hole. At absolute temperature, mass of the electron equal to mass of the hole. Okay, hence the equation will become, Hence the equation will become, so what happened? EF is equal to EV plus EC by 2. EV plus EC by 2. That means Fermi level is at absolute temperature. So absolute temperature means T is equal to 0. If you substitute the T is equal to 0, so what will become? EF is equal to EV plus EC by 2. Okay. So now what is the EF here? Fermi level. So Fermi level is exactly middle. Exactly middle. That means at absolute temperature, that Fermi level value is so middle of the valency band and conduction band. Valency band and conduction band. Now, if you increase the temperature, what happens? Fermi level also increases. Okay, yeah. Thus, the Fermi energy level EF is located in the middle of the forbidden band at absolute temperature. At absolute temperature. That means absolute temperature is nothing but at 0 Kelvin. So that Fermi level is see here. So Fermi level at 0 Kelvin. So Fermi level is exactly middle. What is the reason? Means at Fermi level, mh mass of the hole is equal to the mass of the electron. That's why. So that Fermi level value is exactly middle of the valency band and conduction band. Valency band and conduction band. Okay. That means EF is equal to what we can write. Middle is nothing but EF plus EC. Sorry, EV plus EC by 2. EF is equal to EV plus EC by 2 at absolute temperature. Now, if increasing the temperature, what happened? See here. Now, so if increase, so I will explain by using another graph here. Yeah. So if increasing the temperature, EF value is increases like this. EF value is increases like this. Okay. So these graphs are not suitable to, no need to you. Okay. So I will explain you. So these graphs are not required for you. Okay. So that means with increasing the temperature, just so like this, it will be increases like this. It will be increases like this. So I will send that graph in your material. Okay, how it will be increases with increasing the temperature. So these all graphs are not needed. Okay. Now this is the energy Fermi gap value. Fermi gap value. Okay, this Fermi-Dirac function also not required for you. Okay, here it will be seen that. So EF, this is the EF value 3 kT by 4 into ln of mh star by me star plus EV plus EC by 2. Okay, now here EF is proportional to temperature. EF is proportional to the temperature. Now how it will be, see here. Okay, see this graph. Okay, now EF. So with increasing the temperature is on x-axis. So energy on y-axis, if you will take, means if increasing the temperature, what happen means that Fermi level will be increases like this. Fermi level will be increases like this. Okay, see here. So that means at a higher temperature, mh value, so mass of the hole is greater than the mass of the electron at higher temperatures. So why it will be like this means, so mass of the hole is greater than the mass of the electron at a higher temperature. At 0 Kelvin, mass of the hole is equal to mass of the electron. If increasing the temperature, what happen? Mass of the hole is increases. Mass of the hole is increases. That is the effective mass of the hole is increases with increasing the temperature. Okay. Now, so conductivity of the intrinsic semiconductor. So how we will calculate the conductivity? So conductivity, total conductivity sigma is equal to conductivity of the electrons. So sigma E plus conductivity of the holes. Conductivity of the holes. Already we know that formula, sigma is equal to Ne into mu. Here N is the density of the electrons. Density of the electrons. E is the charge of the electron. So mu is the mobility of the sigma E. So that means due to electrons, what is the conductivity? Due to electron, what is the conductivity? Sigma E is equal to Ne into mu E. Similarly, due to holes. So what is the conductivity here? So sigma H is equal to P is the density of the holes. E is the charge of the hole. Mu H is the mobility of the hole. mobility of the hole. Sigma h is equal to P into E into mu h. Okay, in case of intrinsic semiconductor, so conductivity is occurred due to the holes as well as electrons. Holes as well as electrons. That's why total conductivity in case of intrinsic semiconductor is equal to the sigma is equal to, so sigma E plus sigma h. What is the sigma E value? Ne into mu E. Mu is mobility. Mobility means, so what is the possibility of mobile the electrons? That means mobility is nothing but how electrons will mobile inside the semiconductor. Okay, so that is the mobility. So different material having different mobility values. Okay, for silicon it is different, for germanium it will be different. Okay, so that mobility also depends on the temperatures. Total sigma is equal to sigma E plus sigma h. So sigma is equal to Ne into mu E plus, so Pe into mu h. Okay, in case of intrinsic semiconductor, N is equal to P is equal to Ni. Hence, sigma is equal to Ni into E into mu E plus Ni into E into mu h. Okay, here Ni into E is common for both. Okay, so Ni into E is common for both. Why we are taking Ni means here, so in case of intrinsic semiconductor, N equal to P. N equal to P. So N equal to P is equal to Ni. Okay, we are substituting that N instead of N and P, we are substituting Ni. Okay, so if you will take common, sigma is equal to Ni into E into mu E plus mu H. Okay, now if you substitute the Ni value, already we calculated Ni. Okay, if you substitute the Ni value, we can get the, so density of the, what is that, conductivity of intrinsic is of the conductivity of the intrinsic semiconductor. Okay, now I will take the attendance. If anyone have any doubts means you can ask. Any doubts? Okay, yeah. So if you have any doubts, you can ask. Otherwise, you can leave from the class.